Hello students and welcome to the 22nd lecture on particle physics. In the last lecture we were discussing about Kaon regeneration phenomena and we shall continue with that. What I was talking about, that we have K0 and K0 bar as the production states. Then we have K10 and K20 as the propagation states. But as they propagate, we find that K10 has a longer lifetime and we requisition it by the name KL0, and K20 has a shorter lifetime. We requisition it by the name KS0, and therefore we write K0 and K0 bar in terms of 1 by root 2 KS0 plus KL0 and 1 by root 2 KL0 minus KS0. Now, since strangeness is not conserved in weak interaction, that is why what we talked about, that a K0 may get converted into K0 bar, but that change is a strangeness to change process, and the strangeness by unit 2 change is not a first order process. This is a second order process which can take place with the exchange of two W bosons. Now, in the last lecture, we talked about how this W exchanges take place. Here I am giving you the example where we can have with the help of two W boson exchange, a K0 can get converted into a K0 bar. Now, what we know that a K0 is a strangeness plus 1 particle which is made up of d S bar quark. Now, what is happening? A d is emitting a W minus. As soon as it emits a W minus, it may get converted into either a U quark or a charm quark or a top quark, up, charm and top. All three of them have 2 by 3 units of charges. And now we have S bar which is coming towards this vortex. U, C, T are coming from, or C or T is coming from this vortex. When they will meet, this S bar charge is also plus 1 by 3. This U is 2 by 3. Therefore, we can have a W plus exchange. And then this W plus can give rise to, or yet this W minus can give rise to S U bar quark or S C bar quark or S T bar quark, such that strangeness has minus 1 by 3 charge, U bar has minus 2 by 3 charge. Therefore, the total, mind it, these are anti-quarks. Therefore, in Feynman notation, an outgoing particle is represented by a downward arrow. Therefore, this arrow is in the opposite direction. W minus is emitting or giving rise to S U bar quark, and then when this U bar is meeting with W plus, U bar is carrying a charge of minus 2 by 3 and W plus is carrying a charge of plus 1. Now we have a D bar which has a charge of plus 1 by 3. Therefore, if you notice, 1 by 3 baryon number is coming here, 1 by 3 baryon number is going out. Therefore, we have a K0 particle. Therefore, this is what I was telling you, that if there is a change of a strangeness of 2 units, then that will be a rare process because you need to have 2 W boson exchange, and you can see that either we can visualize this W boson exchange either in this way, or we can visualize this, that a D quark is emitting a W minus. It is getting converted into UCT, which is propagating, and then this W minus is getting absorbed by S bar, and we have a U bar or C bar or T bar. Again, here you can notice that we are conserving baryon number at each vortex and we are conserving charge at each vortex. This is how Kaon can change to K0 can change to K0 bar, or similarly we can visualize that a K0 bar can change to K0. You may do it as a homework, that using quark diagrams you show that how a K0 bar can change to K0, again you will require these two W boson exchanges. Now this simply means that K0 and K0 bar are just the production states, and they propagate in the space as a linear combination of K10 and K20. Now we start with a K0 beam produced at say time t equal to 0, represented by a state psi. That means what we have, a pi minus beam, it strikes a proton target, and we have a lambda 0 and a K0, and then we are propagating this K0 in a space. Therefore, the important point is K0 is now propagating in a space, and K0 propagates as a combination of K10, K20. That is what we have expressed. This is at time t equal to 0. Now, at a later time t, now these kaons propagate as KL0 and KS0, and they are long-lived and short-lived kaon states, but they decay to 2 pions and 3 pions, and that means their lifetimes are fixed. And if the lifetimes are fixed, then recall from quantum mechanics that psi t0 at time equal to 0 evolves with time, such that at a later time t, the time dependent wave function of K0, using time evolution equation, you can look at Schiff's book or any quantum mechanics book, that is given by psi t0 e power minus iet. And this E is now for the particles of definite lifetime is m minus I gamma by 2, where this gamma is known as the width, and this is inverse of the lifetime of the particle. Therefore, you can see that if you look at the proper units, then we have 1 upon the lifetime, and time is here. Therefore, this is a dimensionless quantity. Therefore, the important point is exponential is a dimensionless quantity, as you can find out here also. Therefore, the time evolution equation, we can write this as, for any other time t, as psi, the wave function at time t equal to 0, times e to the power minus iet, and E we are writing for a particle with definite mass m and a lifetime tau. We are redefining it as power minus I m minus I gamma by 2 into t, or equivalently I can write it as psi t0 power minus imt times minus and minus will give us plus, and I square will give us a minus sign, minus e to the power minus gamma t by 2. Therefore, either I can write in this fashion, or simply we can keep this expression. Therefore, we have to keep this in mind, and this psi t0 we have to keep in mind that this is 1 by root 2 k L0 plus k S0, and that is what we are going to exploit. Therefore, we have psi t as power minus iet 1 by root 2 k10 plus k20, which we are writing it as minus I m minus I gamma by 2 t, and this I am rewriting it as 1 by root 2 e to the power minus I m st times e to the power minus gamma st by 2 k S0 plus e to the power minus mlt for the long-lived kaons, e to the power minus gamma lt by 2 kl0. Now notice, if I can take e to the power minus imst outside, we have e to the power minus gamma st by 2, and this minus imst, since I have taken common, this guy will go here with a positive sign. Therefore, this is minus I ml minus mst to the power minus gamma lt by 2 kl0, and this ml minus ms, we are calling it by the name delta m, and we will see the significance of this delta m, as I have pointed out that K10 is not the anti-particle of K20, or KL0 is not the anti-particle of KS0. Therefore, in principle, their masses can be different. Now, this as you notice, we have Ks0, we have KL0. Now this we are rewriting it as in terms of K0 minus K0 bar and K0 plus K0 bar. And this is what we have done. We have reintroduced 1 by root 2 K0 minus K0 bar for this fellow Ks0, and 1 by root 2 will give us 2. Therefore, we have 2 outside, e power minus gamma st by 2 K0 minus K0 bar plus e power minus I delta mt power minus gamma lt by 2 K0 plus K0 bar. This is an equation which we can further look at, and what we find out that probability of observing K0 after a time t, the well-known quantum mechanical equation, will be given by this expression. And if I write this expression, this is equivalent to this guy. And if you notice that if we are doing something like this, then we have the power minus imst by 2. We have to take the mod square of that. Therefore, this guy with mod will go away, and we will have 1 by 2 square, that will give us 1 by 4. Then we have minus gamma st by 2 square, that will be minus gamma st. Now, this is K0, 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 K0 bar, K0, K0, and K0, K0 bar. We are talking about probability of survival of K0. Therefore, these are orthogonal states. Therefore, they are not going to contribute. They will be 0 and this will be equal to 1. Therefore, you notice that what we have, power minus gamma st plus e power minus gamma lt, because here also we have power minus I delta mt and then power minus plus I delta mt. Then we have to take this quantity and conjugate of the second fellow, and then this quantity and the conjugate of the first fellow. It is something like mod of psi 1 square plus mod of psi 2 square plus psi 1 star psi 2 plus psi 2 star psi 1. This is what we are supposed to get. Now, if you notice, that means we have 4 terms. The first term we have written here, K0. The second term we have written here, power minus gamma lt. Now we have this term and the conjugate of this term. Therefore, conjugate will have a plus sign here, power plus I delta mt, as you can notice, and power minus gamma lt by 2 power minus gamma st by 2. I am combining this. I have written like this. And then now we have the conjugate of this term and this guy. This guy is with a minus sign. Therefore, it power minus I delta mt. While these are without i's, therefore this will give us the same result as what we have got in the third case. Therefore, this is the simple result when we want to have K0 that is remaining as K0. Now recall, we have discussed that the short-lived kaon has time of 89 picoseconds, while long-lived kaons have a lifetime of around 51 nanoseconds. Therefore, long-lived kaons live much longer. Therefore, tau s is 1 by 570 times tau L. That means tau s is a very small value. And if tau s is a very small value, that we will look at it, this will give us, in principle, gamma tau s almost equal to 1. And this will result us, as you can see, gamma tau s is almost equal to 1. First, we are writing it as e power minus gamma st plus e power minus gamma lt plus this quantity we are treating as 1. We will have 2 e power minus gamma L by 2 into t times cos delta mt. We should also put this as equal to 1. 1 plus e power minus gamma lt plus 2 to the power minus gamma L by 2 into T cos delta mt. Cos delta mt, as you can see, we have e to the power I delta mt and power minus I m delta t. We are multiplying by 2 and divided by 2. This is because gamma S has gone. Gamma L by 2 into T is also only there. Here it is there and here it exists. We are taking that common and we have 2 into power minus gamma L by 2 into T times cos delta mt. Now, similarly, you can find out what will be the probability of finding out K0 bar in the beam of K0. Now, notice here we found out K0 survival probability, and the next time what we are doing, we are finding out that how many we will have K0 bar, and as you can see that when we will take K0 bar here, then that means I wish to have this thing to evaluate. Now the terms with K0 bar, K0 and K0, K0 bar, they are orthogonal states. Therefore, what we will have, again we will write this in the same form as K0 bar psi t times K0 bar psi t star. We will have 4 terms and we will solve that. You will see that this time we have power minus gamma st plus power minus gamma lt minus, here there will be a change of sign, while in this case we had plus sign, while interference sign had the plus term, and here the interference has negative sign. Therefore, this is the change. Otherwise, you look at it, all the terms are the same. Therefore, the probability of K0 to K0 is plus here, while probability of K0 to K0 bar is here with a negative sign. Now, if the same algebra you repeat if you have a pure K0 bar beam, and then that you propagate and you say that this K0 bar beam will actually propagate as a combination of K10 and K20, and for that matter that will propagate in terms of the long-lived kaons and the short-lived kaons, what you will realize that the probability of oscillation of K0 to K0 bar would be the same as the probability of oscillation of K0 bar to K0. Or equivalently, if I say that probability of survival of K0 to K0 will be the same as probability of survival of K0 bar to K0 bar. This is what we have written here. Now, if I plot time and intensity, then probability of neutral Kaon oscillation represents the survival probability of K0. As you can notice, at time t equal to 0, we had started with a pure K0 beam, and at that point K0 bar was 0, but as the time progresses, we have a linear combination of K0 and K0 bar, and this will be true for K0 bar also. And then in the next picture in dash, which is shown by dashed B line, represents the oscillation probability of K0 to K0 bar. Therefore, this is the survival probability of K0 to K0, and the dashed line is the oscillation probability of K0 bar, K0 to K0 bar. Similarly, the such type of graph you can get it for K0 bar remaining as K0 bar by A, curve A, and K0 bar oscillating into K0, you can show it by curve B. This is for fixed delta M. That means your delta M is not equal to 0. Now, if you change this value of delta M, put the different numbers, this delta dashed line will change. And as you can notice from the previous curve, that if your delta M is 0, then this quantity is 1, and you have this expression minus gamma st plus power minus gamma LT minus 2 e to the power this factor. That means this delta M will tell you that how the oscillation probability will change for K0 to K0 bar if you have different values of delta M. That means experimentally we measure the oscillation probability of K0 to K0 bar, and from there we determine that which value of delta M can best describe the experimental data. Therefore, what I am telling you that you have this dashed line, you go back to the experiment, you will have another line for some value of delta M, another line for some value of delta M. Therefore, you have 3-4 values for delta M. What you do, you go back to the experiment and see that what is the oscillation probability when you have a pure K0 beam, and the best experimental data that passes through this line can give you the number of delta, what the value of delta M you should take. Now the intensity of K0 bar, as you can see, rises from 0 and shows oscillatory behavior. You see, this is not constant, this is showing oscillatory behavior with the same frequency. Using the observed data for oscillation, the mass difference is found to be 3.52 into 10 power minus 12 million electron volt. As you can see that the mass difference is very, very small, but that is finite. Therefore, and this has been observed by plotting this probability and using the different value of delta M, and the best value that fits is 3.52 into 10 power minus 12 million electron volt. It has been observed experimentally that with the recent experiments that the mass difference is, as I have told you, is this much. You can see that the accuracy, we are achieving better precision in this mass difference. As you can see that the error bars are also small. Since delta M is a positive quantity, therefore it implies that short-lived kaon is less massive than the long-lived kaon. That is another important catch, that ml minus ms is a positive definite quantity. Therefore, this implies that ml is greater than ms, and in turn that what we are saying is that mass of short-lived kaon is smaller than mass of long-lived kaon. Now, this complete thing we can visualize in this figure, and this is a beautiful figure which will convince you that really kaon K0 is getting converted into K0 bar. What we have done here on the extreme left, we have pion beam, pi minus beam, and that strikes proton target. And pi minus beam, when it strikes proton target, we know that we can have a lambda 0 and a K0. Now this K0 starts propagating, as we know that that is proportional to K10 plus K20. This is proportionality 1 by root 2 normalization factor. Now instead of K10, K20, we again rechristened it by the name KL0 and KS0. Now KL0 is decaying to 3 pions, KS0 decaying to 2 pions. Therefore, after some time, what will happen? We won't have any KS0, we will have only KL0 component, only the long-lived kaon component. Now this long-lived kaon will start propagating, and it will propagate in terms of again combination of K0 and K0 bar. Long-lived kaon is propagating as a combination of K0 and K0 bar. Now in the experiment, it has been found that if we put a target, a nuclear target, where we can have a proton or we can have a neutron, a thin nuclear target, then what has been observed that in the final state, we have a lambda or pi plus, and we have a lambda or a pi 0. Now a lambda and pi plus or a lambda and pi 0 cannot be produced by a K0, because K0 bar is strangeness minus 1 particle. Lambda is a strangeness minus 1 particle. You have the conservation of strangeness quantum number here. This is a strong interaction process. The second one is also a strong interaction process. Therefore, what you are finding out that K0 bar is interacting with the nuclear target and you have a lambda and a pi plus, which was not possible through a K0b. Therefore, you have seen that you have started with a pion beam that strikes proton target. You have K0s and that K0 is propagating in space, and then you have only the long-lived kaonic states, and that long-lived kaonic state is a combination of K0, K0 bar state, and then that K0 bar, though you have both of them, but when it strikes the nuclear target, K0 cannot produce a lambda and a pion, while K0 bar will produce a lambda and a pion. This is a strong interaction process. The chances of this process will be very likely. And if you are observing these two processes, then that means a K0 has got converted into a K0 bar. This is what we know by the name Kaon regeneration. And now from here, then I will talk about how from the experiments it was concluded that CP gets violated in the neutral Kaon sector. Let's stop here. We shall continue the discussion from this point. Thank you very much.